Hi, I'm Carlos Mendoza, a PhD student at the Electrical and Computer Engineering Department at the University of Delaware. I'm working with Dr. Austin Brockmeyer, and in this talk I will explain our work titled Shift-invariant waveform learning on epileptic ECoG. So what we did was to develop a method that learns a codebook of centroids from the preictal and interictal state of an epileptic ECoG recording. We also call these centroids prototypical waveforms, as they approximate the repeated occurrence of stereotype non-sinusoidal waveform shapes across the ECoG recording. We evaluated the quality of these codebooks through a binary classification task and the predicted performance of each individual waveform through a statistical test of independence. Why should you care? Well, the waveform shape of neural oscillations matter. In this work by Cole et al., they define the sharpness of peaks and troughs of neural oscillations and found that for Parkinson's disease patients, the deep brain stimulation reduces the sharpness of the peaks more than the troughs. More importantly, the sharpness ratio is highly correlated with the modulation index, or PAC, the phase amplitude coupling between the phase of the beta oscillations and the amplitude of the high gamma oscillations. This highlights that the analysis of the waveform shape could be used as a complementary tool to the traditional spectral analysis of PAC. In this work by Liu et al., they found that for high-frequency oscillations, or HFO, coming from the seizure onset, they are more correlated between them than HFOs coming from electrodes out of the seizure onset or electrodes in the functional areas. This is depicted here in these graphs of similarity, where each node is a waveform, and the darker the links, the more similar are the waveforms. This waveform shape similarity could be used to blindly identify the seizure onset zone. There are some works that are related to our work. These two works uses a convolutional dictionary learning approach to learn recurrent waveforms for EEG. This work by Brockmeyer and Principe learns recurrent waveforms across different time scales for each EEG channel independently. And this work by Latour et al. Learns a multivariate dictionary of waveforms with a rank 1 constraint, meaning that the spatial pattern is fixed for each temporal waveform. In this work by Kuit et al., they use a k-means algorithm to build a codebook of waveforms from the interictal and preictal state of an epileptic recording for seizure prediction. However, in contrast to our work, there is no shift invariance built into their method, which can lead to codebooks that have waveforms with similar shapes but occurring at different time shifts, as is highlighted here in these red and purple boxes. So, how we did it? Now I'm going to explain in detail our methodology, and I'm going to start with the data. We use multi-channel, multi-day epileptic ECoG data from 4 patients from the IEEG.org platform. We applied a pre-processing pipeline that is described in this paper, and after that we split the data in 2 segments, interictal and preictal segments. The preictal segment is 1 hour long, just before the seizure or the ictal zone, with a 5-minute intervention gap, and the interictal segment is anything that is 4 hours away from the ictal zone. Let's talk now about our shift-invariant waveform learning method. Here we show the main blocks that are involved in learning a codebook of prototypical waveforms from a set of non-overlapping windows of multi-channel ECoG data. The windows are spatially filtered, and after that a shift-invariant k-means algorithm learns a codebook of centroids that best approximates the spatially filtered signals. For the spatial filtering step, we use the common spatial patterns method to compute 2 spatial filters, W0 and W1, such that they maximize the variance of the data in one class, preictal or interictal, while minimizing the variance in the other class. To estimate the covariance of the interictal and the preictal data, the multi-channel ECoG data is temporally filtered in these 9 spectral bands. We build the precision and recall core of a binary classifier that uses the energy of the spatially filtered data to estimate the segment class. We pick the two spatial filters corresponding to the spectral band with the highest average precision for the rest of our pipeline, with the average precision being the area under the precision recall curve. Let's talk now about our shift-invariant k-means algorithm. We call it shift-invariant because the signals in the data are of length L, and we want to find a set of k centroids of length p smaller than L, and the time shift that best matches the centroids. We start by drawing at random a set of centroids from the data, taking the p-length window with highest energy, and then in the cluster assignment step, we use the cosine distance to find the centroid that best matches each signal and the best time shift. This is an example of the cluster where the centroid is the kth centroid. Then, in the centroids update step, we take the p-length window that starts at the best time shift for each signal in the cluster and average those signals to update the centroid. We iterate over the assignment step and the centroids update step until the change in the centroid is smaller than some threshold. We want to evaluate the quality of these two class-specific codebooks through a binary classification task. To do that, we split an ECoG segment into m consecutive non-overlapping windows and spatially filter each window using the spatial filter optimized for interictal data and the spatial filter optimized for preictal data. We then assigned each signal to its closest centroid from the codebook class that matches the spatial filter that was used in each path. After that, we use a backwards approach to count the number of times that each centroid occurs in the data. We then concatenate the centroid counts from each codebook into a single feature vector. We then use the feature vectors and the true labels in the training set to train a classifier that will predict the class of a test ECoG segment as either preictal or interictal. We tested several classifiers, among them the multinomial naive Bayes and the logistic regression. We use a tenfold cross-validation with the Matthews correlation coefficient as the performance score to select the number of centroids, the centroid length, and the regularization parameter C for the logistic regression classifier. We also evaluated the predicted performance of each individual waveform through a statistical test of independence. To do that, we concatenated the interictal and preictal codebooks into a single master codebook, and then assigned the signals in the interictal and preictal class to the centroids in that master codebook. We then count the number of times each individual centroid in this concatenated codebook occurs in the preictal and interictal class. With those counts, we build a contingency table for each individual centroid in the master codebook. And from this table, we compute the chi-square test statistic for each individual centroid in the master codebook. Here we see an example of this. Okay, let's go now through some of the results that we got. This is a sample of the prototypical waveforms from the preictal and interictal state that we learned for a specific subject, number of centroids and centroid length, with the centroids going in descending order of chi-square test statistic from left to right and top to bottom. Let's now see the results that we got for the binary classification task for the two classifiers and the 4 subjects. We got a high classification score for one of the subjects and medium to low performance for the other 3 subjects. And in-depth inspection of the data and the centroids that were learned might be needed to fully understand the reason behind such variability. Finally, we want to point out that our method can be seen as an scalable summary of a time series, where the summary is given by the codebooks and the waveform counts. The centroids are suitable for physiological interpretation, since the only transformation in the data is the spatial filtering. And as we saw in the results, these interpretable features can also be discriminative of the preictal and interictal state. We could improve this work by adding more CSP filters, filter the data to find high-frequency oscillations that are masked under low-frequency oscillations due to the 1/f spectrum of the data, and consider the cases where the number of centroids and the centroid length are not homogeneous. Thanks for attending this talk and check out our code.